It's being recorded, right? So that's for my reference. Okay, so what we have been doing is the following. Okay, so we started with the self-adjoint operator. So X is in B of H self-adjoint. Then we, for any polynomial, so then let sigma X be the spectrum. Then for any polynomial P, and this revising on sigma of X, we can define P of X just by substituting. And we know that this preserves the norm. This mapping going to P going to Px. P is the polynomial with C of sigma X norm. Okay, C of sigma X is a compact subset, and it has a norm, uniform norm over that. These two norms, this is isometric. This mapping is isometric. So we can extend this map to the closure of that, which is C of sigma of X. Okay. So this extends C of sigma of X to some, into B of H, which is actually C star algebra generated by X and 1, whatever. One will be there mostly. So yeah, it's a C star algebra generated by X. If you want, even just for safety, you can add 1. You have to prove that 1 is there. So is this it? So because this is the smallest C star algebra because it contains all the, any C star algebra should contain the polynomial. So this is the smallest C star algebra, and it is just the closure of that. So it has to contain that. So this mapping we call some f continuous function here, which going to f of x is what we call as continuous functional calculus. Okay. This continuous calculus can be further extended to it can be extended to some L infinity. So there exists a mu which is unique up to mutually absolutely continuous, such that we can extend to L infinity mu of sigma x to this. This is not, I will not say what it is. This is actually what is called a von Neumann algebra. Okay, this is not C-star algebra. This will be something bigger than that. You have to take the closure. It is just you take the closure in the strong topology. Okay, it's precisely that. And and another thing is this mapping, whatever this functional calculus is unique. You have this f naught, which is equal to f naught of t. You have this function. You have this polynomial, which is f naught of t equal to the identity polynomial. This will go to x. Okay, and then the polynomial t square will go to p of x, and polynomial in t will go to polynomial in x, and that's how this completes. So the map is unique. Okay, and similarly we have a L infinity from L infinity to b of h into b of h. Okay? This is into b of h. This is also, of course, we denote by f of x to f of x, and this we call it as measurable functional calculus. Measurable functional calculus is just an extension of the continuous functional calculus. But then you remember measurable functional calculus is defined, measurable functions are defined up to almost everywhere. Okay, so two functions are equal almost everywhere, then their operator should be equal. So that's one thing. And it's also an isometric. And it further satisfies if you have a Fn converges to F, norm Fn uniformly bounded, and Fn converges to some F, and the convergence is in some measure. In particular, if you have almost everywhere convergence, that will imply in the convergence in measure. Then this Fn of x will go to f of x in the strong topology. Okay, so that's what we have done. So that's what you have to understand. So what is nice about this strong topology is whenever we have convergence in projection, sequence of projections or something, then the projections, they won't converge in norm. Usually they will not converge in norm. So, because if you take some bigger projection, and suppose these projections are increasing to something, I minus Pn is also a projection. So this will have norm 1. This can never go to 0. So norm convergence will not happen in projection most of the time. I mean, unless you have some funny thing. So, I mean, you can arrange to make it, but it's most of the useful convergence and projections are strong convergence. Okay, so that is why this is very important. For example, you can take one particular strong convergence. So we can, for any L infinity function, we can associate an operator which we call as measurable functional calculus. In particular, if we take the indicator function, this is just indicator function. So this corresponding to that, you have this. And such a function is a projection because this function, whatever this 1 e square equal to 1 e bar equal to 1 e. So this is because of that, this is a projection. So this becomes a projection. Because of this property, this is an algebraic homomorphism. This is actually a projection. Is a projection. So suppose you have some sets. Suppose some En set such a and E such that mu of I think this will work. E minus En E minus En goes to 0. Suppose this happens. Then what does it mean? Then I want to claim that 1e, the function 1e converges to 1e, sorry, 1en converges to 1e in measure. So let us consider this. All those set x such that. So this is the definition of convergence in measure. 1e minus 1en. But 1e minus 1en is again this greater than epsilon is what we want to consider. But then this can take the value 1 or 0. I mean, it cannot be anything else. So wherever this takes the value 1, so which is basically mu of wherever it, when will it take the measure? That will take precisely when mu of E minus En is, I mean, this is precisely equal to mu of E minus En, right? That's where it takes the value 1. So that is where, that's what this mu is. So this goes to 0. So 1e, this function, 1en goes to 1e. This will certainly happen if almost everywhere convergence also for almost function which converges almost everywhere. So 1en converges to mu in 1e. So this implies 1en x. This is functions, okay? This is functional convergence. 1en converges to 1e is functional convergence. This is operators. 1en of x converges to 1e of x. Projections, strongly. Okay? So we got a strong convergence. So that is how this, I mean, that is how this measurable functional calculus is important. These are all not continuous functions. So you cannot use continuous.
So like where this 1ex projection? I mean, like how will the images be closed?
1e is a projection. It's a projection. Any projection is closed. What do you mean by how is it closed? I'm not talking about subspace. I'm talking about projections. Projection,
I mean,
any operator P which satisfies P equal to P star equal to P square. Such a
oh,
range
I
of
see.
projection is always,
Yeah.
that's always closed. You can check it is closed. Okay. So which we have done all these things. So because of that. So this 1e satisfies the condition of projection. It as a function, it satisfies 1e equal to 1e bar, which is a star there, and 1e square. This is an algebraic isomorphism. Okay, this measurable functional calculus is an algebraic isomorphism. So I mean, it preserves the product, it preserves the star, everything. So because of that, the 1ex will satisfy the corresponding, the idempotent condition, the self-adjoint idempotent condition. Self-adjoint idempotents are the projections. Okay, so that's why we get projections. These projections for E contained in, for E not contained in E Borel's sigma of x, this 1E, whatever we have this, these are what are called, so spectral projections. Okay, for any spectral Borel subset of a spectral spectrum, we get a projection. These are what are called spectral projections. As you can see, all these spectral projections commute because the functions commute. So all these 1e and 1f will commute. Not just they commute with all measurable, I mean, all these functional calculus, they commute. Okay, this is a commuting set of operators associated to this x. Okay, anything in this x is a self-adjoint, so it generates a self-adjoint C-star algebra. Okay, sorry, it generates a commutative C-star algebra, and all these things commutes with each other. Okay? So in particular, X will commute with all these spectral projections. Okay. Okay. So we were proving the following proposition. We were in the middle of it. So it was the first one we have already proved. First one is if we take the spectral projections are defined for a subset of E, a subset of sigma of X, which you can extend to any subset of C or R. I mean, X is self-adjoint here, so the spectrum is contained in. So sigma of X is contained in R. Okay. So now, for any subset of R, you can define a spectral projection just by taking the intersection with the spectrum. Okay, that's what we did. That's what we defined in the last class. So this is just for our convenience. A spectrum is just a compact set. A compact set can be any, I mean, maybe complicated, but we want to associate for any interval. So we just take, especially bounded interval. So you just take the intersection with the spectrum and then define the corresponding spectral projection. That's all. Okay. So we want to prove the following things. We already proved it. So the first thing is if X is in. So we defined. I mean, this is just the notation in the book by Sundar, the operators on Hilbert space. So MXE is the range of this projection, 1EX. Okay. I mean, this notation is flipped, so you may get confused sometime. We go fast. Okay, here X is in the subscript space, and E is here. Here the E and X are interchanged. But that is the right notation. 1E of X is the right notation because 1E is the function and 1E of X. Okay, so that is the right notation. Here he is using this, so I am using this because it will be convenient for you to read the book. Okay, now we have the proposition. 1. So this is for all these things are for a self-adjoint operator. X is X star. Okay. Now first statement is if X is in M, the interval AB, here it should be X. X of AB is closed interval AB. Then A norm X square is less than or equal to XXX. So that is in the range of the projection is less than or equal to B times norm X square. Okay. We have proved it. We proved it. This just follows from the property of the indicator function. The indicator function 1AB times X times T. T is less than or equal to B, greater than or equal to A times T. A times times T. Times T is not needed. No, A times 1AB, sorry. But yesterday I wrote it correctly. Can become 0. So what did happen? A times 1AB, if I write, 1AB is fine. Yeah. You are just going to apply it to. There the T is there, here the T is not there. Okay. Yeah. This is okay. This is correct. As functions, this is true. Okay. This is true for all T in the real line. Okay. So from that it will follow. And we proved that the measurable functional calculus, whatever, any homomorphism, any representation or any homomorphism in C-star algebra preserves the order. If some operator, so by some operator is greater than something, we mean that, that's defined only for self-adjoint operators. Okay. So some operator is greater than something if the difference is greater than 0, which means the difference is positive. And we define positivity for operators. Using that, we define the partial order on self-adjoint operators, not on all operators, only on self-adjoint operators. That's where it makes sense. So using that, this positivity is preserved by any homomorphism. Because of that, it follows. Okay. The second statement is just the restatement of that, which is X times 1, 0 infinity of X is greater than 0, right? Yeah, it is just greater than 0. Which is just clear. Okay. Which is just says that, if you take A to be 0, it's just greater than 0. So that's what it means. You just take A equal to 0. Okay. Third statement. Third statement also we proved, right? Yeah. So for that I gave an assignment. Okay. Third statement is for all epsilon greater than 0. Okay. Um, for all epsilon greater than 0, yeah, x minus t0 x is greater than epsilon times log x. T0 is the spectrum. T0 is any number. T0 is anything. Okay, and x is there. T0 is any not epsilon be greater than 0. Okay. Then if you have x, mx in T0 minus epsilon, T0 plus epsilon in this interval, okay, in this range of this projection, then x minus T0 x, the small x, norm is greater than epsilon by norm x. Okay. This is true for all this. So this we proved by using the first statement in this. So it follows that this projection, we want to consider this projection, mx of this. I mean, I gave you an assignment. Mx of E is same as m p of x of p of E for all polynomials. Okay, this was an assignment. Once you do this assignment, this is just clear. Use spectral mapping theorem to prove this. Okay. Then because of this, this is same as so x minus. I mean, we proved something for x. Now we apply that to x minus t0 divided by epsilon. So it will just follow from that. Okay. I mean, that will have the range epsilon square to infinity, and because that will this whatever this square is greater than epsilon square times lambda square. Okay, so because of that it will follow. We are applying that to x minus t0. Okay, and x will be in the corresponding projection of that in epsilon square to infinity. You just apply it to that, you will get this. You have done this yesterday. And the third one is if the T0 in this, then this is about the spectrum. These four terms. T0 in the spectrum of X. Then for all epsilon greater than 0, mx of this is closed, I believe. T0 minus epsilon. T0 minus epsilon, or I think it's open. Okay, so let's see. It will matter. Okay, single point terminal will matter. So you should be careful about this. This is not equal to 0. Okay. So some T0 is in sigma the spectrum. If you take any epsilon, you take the epsilon neighborhood around T0, then the spectral, I mean, every interval has a spectral projection. The spectral projection corresponding to that interval is not 0. Okay, that is the condition. Proof. What does it mean by some T0 in sigma of x? This is equivalent to saying x minus T0 as operators is not invertible. Okay. This is equivalent to saying this function f0, whatever we have, f0 minus t0, f0 is the f0 of t equal to t, the identity polynomial, the polynomial 1 degree polynomial f0 t equal to t is not invertible. I mean, we can consider the invertibility in C of x or in L infinity. For our purpose, because we want to do something with projection, we have to consider the invertibility in L infinity. I mean, the L infinity, it is just it's defined up to almost everything. Okay, it is that the recurrence class is not invertible. That has a different meaning. Okay, I mean, this function is not invertible in C of x. That just means that T0 is in the range of f0. So T0 has to be the T0 in sigma of x. That's what it says. T0 in sigma of x is same as F0 minus T0. F0 is just the identity function. So it has to be in the range of F0 means T0 has to be in sigma of x. Okay. It is just the identity function of sigma. So it's in the range of that. That's what it means by the something is not invertible. Something is not invertible means you should not be able to define 1 by f naught. Okay. That is not possible if T0 is in the range. Okay. That's all. I mean, sorry, if T0 vanishes in the range. I mean, if you have a function that is not invertible, if it vanishes, okay. Now, f naught minus T0 is not invertible means f naught minus T0 should vanish. That means T0 should be in the range of f naught. The range of f naught is just sigma of x. So T0 should be in sigma of x. Okay. This is for C of x, invertibility in C of x. For L infinity, so this is not invertible in L infinity with respect to some mu. Okay. So that is also true. That is equivalent to, we saw in the early, I mean, so someone also remarked that why, when we want to prove the isometric property of the map, the representation, we did some, I mean, we used something in the last semester, but here we did something else. But here we did something else because the reason is, one of the reason is we can describe the spectrum. Here went through the spectral radius. So to determine the spectral radius, we determined an equivalent condition for something being in spectrum. Okay, so that I'm using it here. So that's one reason I did that. Okay? You can take it like that. So this is not invertible is equivalent to saying mu of, this is what precisely I prove, mu of this set x such that f naught, sorry, let me do t such that f naught of t minus t naught less than epsilon is greater than 0 for all epsilon. This is precisely I prove. I mean, the proof is we are, so if something is in the spectrum, something is not invertible. Did we use? No, this is no. This we went through the L infinity. I mean, we defined L infinity through something and we proved it. Okay, you just look at the proof. Okay, or you can prove. You can write. I mean, this is something is invertible. Here I write it. Some function, for some function f naught minus t naught is invertible. That is equal to saying there exists an epsilon naught such that f naught t minus t naught this greater than or equal to epsilon naught mu of this. Okay, this is true almost everywhere, right? This is I mean, this is true almost everywhere. This is the definition of invertibility. Then you can write, then you can talk about 1 by f of t. I mean, 1 by this function. Or if you, I mean, if you just take a function, single function, okay, f is invertible. Maybe I'll write it in the bracket there. This is a exercise you can do. Notice a function f in L infinity mu is invertible if there exists an epsilon not greater than 0 such that mu of this t such that f greater than epsilon is equal to 1. This is almost everywhere it should be true. Epsilon naught should be equal. Okay. Or if it's greater, I mean, if it is, that is equivalent to saying mu such that t such that mod f less than epsilon. Okay. Less than epsilon naught equal to 0. Okay. So you check this. This is the invertibility in L infinity. Okay. So I am just using that. So now this just says that one of this, whatever that interval. So what is that? This just says that, so this just says that for all epsilon greater than 0, this mx, then let me write it. Mx of let us write it as a function. 1, I'm just writing it as a function. 1 t0 minus epsilon, t0 plus epsilon. Okay, this function is not equal to 0, right? This f naught t is just t. Okay, so this is just, right? F naught t is the function, f naught t equal to t. Or you just write t minus t naught is less than epsilon. You want. Okay. This is equal to t. So that measure is greater than 0 means this as a function in L infinity. I mean, this is not something. As a function in L infinity, this is not 0. If the measure of that set is 0, as a function in L infinity, this is 0. As a function in L infinity, this is not 0. That's what it means, right? So it will be nice if somebody says yes.
Yes.
Yeah. Okay. Thank you. Okay. Okay. So then this is equivalent to saying, I mean, this is just a function which is not equal to 0. Then it's an isometric representation. So the corresponding projection is not equal to 0. Then the corresponding projection means the range is not equal to 0. That's what it means. That means this mx of this this interval. So this is open interval. Okay. E naught plus epsilon. This is not equal to 0. That's all. Okay. That's all. We have proved. Okay. If anybody has a problem, tell me. So finally, in this proposition, the final statement is mx of t0 equal to kernel of t0. This is for all t0, t0. So this is the criterion. Whatever the fourth one is a criterion for t0 in sigma of x. T0 is in sigma of x. If for, I mean, that implies for all epsilon, this is not equal to 0. Not the other way. No, this is true equivalent. Sorry. This is an equivalent condition. That's what we have done. All these statements are equivalent. Okay. So this is equivalent. Okay. Okay. Now the final fifth one. Fifth one is, what did I forgot? Mx of singleton, no? Mx of singleton T naught is nothing but, this is for all T naught. For any T naught in R, it's kernel of x minus T naught. Okay. Of course, if it is invertible, this kernel is 0. So, I mean, this will not be, this is non-trivial if if T naught is in, this is not equal to 0 if T naught is in the spectrum. If it is not in the spectrum, this is 0. It will be invertible and it is 0. Okay. Okay. So now we want to prove this. So let us prove then this is inside that is inside that. Okay. Okay. So let us consider this 1 let x naught equal to 1 x, sorry, 1 t0 set. This notation is confusing. So 1 t naught x, this singleton t naught x, the spectral projections corresponding to this singleton set x, we take it and we multiply with x. Notice that this x and this projection commutes. So you can take this operator here and put it here. It is just the restriction. This is just the restriction. I mean, I don't want to write restriction and all those things. We should avoid English whenever we do mathematics. I mean, like a sentence. This is something restricted to that. I want to write it as a algebraic operator. So that's why this is nothing but the restriction of x to this space. Okay, it's because it commutes. You can put another one here if you want. Okay, because it commutes, you can. This is equal to its square, so you can take it the other side. So and this is just the compression to this space. Okay. Now from one of this proposition, where we proved some inequality, something greater than a something, but that here the interval is closed interval t0 itself. Okay, so all those inequalities equality. Okay, x naught x. Okay? I mean, this is true for all x. Okay, I mean, for all x, once you apply this projection 130x on that, I mean, then you have a projection here also. So this x, I mean, okay, you can write it like this, and this is equal to t naught times norm x square, right? I mean, the first one, very first one. You see this. This is greater than or equal to norm a times x square, less than or equal to norm b times x square. But here a and b, I mean, we are applying to the interval t naught, where a, both b and both are equal to t naught. So this is just equal to t naught x square. Okay. So this is equal to t naught x square. Okay. So this implies what? X naught minus t naught xx equals 0 for all x in H. But then any operator in Hilbert space, complex Hilbert space, is determined by this quadratic form. Okay? You know this. I didn't touch them. I don't know what's happening. So this implies x naught minus t naught x equals 0. What is it? What am I trying to do? X is in the kernel. This implies x is in the kernel of. No, this just implies this operator x naught minus t naught of, you can, I mean, let me write it in a different way. Sorry. This implies this operator x minus t naught times 1. I maybe you can change it if you want. T naught x, t naught of x times x 1 t naught of, I can put it because the x. Okay, this is true for all x in that image, so we need another t naught here. Anyway, you can even forget about this. This is true. 1 t naught x equals 0, right? This follows from that. Okay. I mean, the initial inequality is true for that, no? So because of that, this is true. Okay. So this implies x minus t naught 1 t naught x is 0. This is true for all x. So this is equal to 0. I mean, this is a complex Hilbert space. So if this kind of quadratic bipolarization identity, if this kind of quadratic forms are 0, then the operator itself is 0. So because of that, this is 0. Okay. So this implies this subspace. The subspace is the range of this subspace is mx with this t naught is contained in kernel of x minus t. Okay. Fine. So we have proved one inclusion. We want to prove the other inclusion. Okay. So suppose x is in the kernel of x minus t naught. Okay. Suppose x is in the kernel of x minus t naught. So what does it mean? Yeah. Okay. So x is in the kernel of t naught. Then we have that inequality. Let me look at it. Yeah. So for all x in yeah. So this 3, look at this 3 here. Given any epsilon greater than 0 for any x here in this subspace, where r this interval removed, there this inequality is satisfied. Okay. So if this inequality is not satisfied, then x has to be in the kernel of this. So it has to be in the orthogonal complement of this subspace, right? Suppose x minus t0, small x is in the kernel of x minus t0, then this norm is 0. So x has to be in the kernel of x has to be in the orthogonal complement of this, right? If x is in this range of projection, x is in this range, then that means this inequality has to be satisfied. If x is something non-zero, x is 0, there is no problem. Then there is no point. If x is in some non-zero vector, which is in this range of this projection, then this inequality is satisfied. Okay, but then x is in the kernel of x minus t0. Suppose x is in the kernel, small x is in the kernel of capital X minus t0, the kernel of that. That means it cannot be 0. It has to be. It cannot satisfy this inequality. So it cannot be. It cannot be in that range. It has to be in the orthogonal complement of that, right? Correct. So I will write it here. Suppose here, then x minus t naught x equal to 0. So it cannot satisfy this inequality. Cannot satisfy. Maybe we'll write it. Satisfy x minus t naught x greater than or equal to epsilon norm square for x not equal to 0. Okay. Okay. So this implies x is in mx of. So the statement is for r, the interval removed from epsilon t naught. Oops. Zero t0. Yeah. Yeah, that is true for all epsilon. T0. I'm sorry if it is confusing. This is right. Please tell me if it is all right with everyone. If x is so, I want to prove this implication. So I prove that the other implication is not true. The reverse is if x is not in this, that has to be in the orthogonal complement. The orthogonal complement, this mx of T naught minus epsilon, T naught plus epsilon. Its orthogonal complement is mx of, I mean, this is just a set, okay? If you have a sum set, 1e is a projection. 1e of x is orthogonal complement. The range of this orthogonal complement is 1e complement x, right? Okay, just think about it. Okay? I mean, which is just one orthogonal complement. If you have a projection P, the projection representing the orthogonal complement is 1 minus P. So 1 minus of this is 1e complement. Okay. So that makes it clear. Okay.
Yeah.
Okay. So because of that, the mx, this orthogonal complement of that range is going to be just, you have to take the complement, set complement, which is just this T0 minus epsilon, T0 plus epsilon. Okay. So it is just that. So something is in the complement. Suppose if it is in the complement, then it cannot satisfy this. I mean, that will satisfy this inequality for each epsilon. I mean, for this epsilon. So that implies it cannot satisfy that equal to 0. I mean, it cannot satisfy that equal to 0. Because of that, I am concluding it is in this for all epsilon. Okay. Now this set 1 minus T0 minus epsilon, T0 plus epsilon. Okay. This function converges to 1 T0, singleton T0. Okay. Is clear as epsilon goes to 0. Or you can take a sequence if you want. Okay. I mean, if you want to work with sequences, you can intercept that. It is in fact that this is also true. Mx of T0 minus epsilon, T0 plus epsilon. This is, I mean, whatever we have said, that is true for all epsilon. So you take the intersection over all epsilon greater than 0. That is equal to mx of T0, singleton T0. This is because if you take the corresponding functions, that goes to this in mu. Okay. Right? I mean, it goes in almost everywhere. Point-wise, it goes there. Okay? So this corresponding projection converges strongly. Okay, strong convergence for it, and this is a decreasing sequence of projection. Decreasing sequence of projection, the strong projection, the limit is just the intersection of the limit. Okay? If some subspaces, some H contained in Hn contained in H, and Hn are subspaces which decreases to some H naught. Okay, then the Phn will converge to Ph naught strongly. Okay, you can verify this. You can apply to each vector and you can verify this. This is a strong. This will not be in norm convergence because the difference will be a projection, again a projection, and that will be of norm 1. So it will not converge in norm. It will converge strongly. If you apply on any vector, then you can write it as some orthogonal complement, this, that, and it will work. Okay? Similarly, for increasing one also. If you have subspaces which increases as subspaces, okay, then the corresponding projection will converge strongly. I think we have seen it when we were looking at compact operators. Okay, we have seen this. Given any, we have identity 1, we have finite rank projection increasing to identity 1 strongly. So we have seen all these things. So I'm just using that. Okay, so what I have proved that X is in the intersection of all these things. So X is in that. Okay, so we have proved the other way. So whatever, these are all digression. These are all digression. So here we are just using it here. From there we get that X is in that intersection. X is in Mx singleton T0. Okay, that's what we want to prove. If we that just we want to prove. Kernel of X minus T0 is contained in Mx of T0. Okay, that's what we want. I hope this is all right. Otherwise, you look at the book. I have given more explanation here than what is written in the book. Unfortunately, it's not written about he hasn't mentioned about strong convergence and all those things. So I think the book there is some. It's I have to talk with Sundar. There are some other problems also. The positivity is defined later, but it is being used here again and again. So I think that's not correct. So that also one turn us to. So I will talk to him later. So anyway, so how much time we have? Okay, so let me prove the next proposition. Next proposition is the following. Okay, so this is the famous criterion of Holmos criterion. Okay, we will call it Holmos criterion. X equal to X star, then I mean some self-adjoint operators. The following thing is true. Then the following are equal. 1, some small x is in the projection, is in the range of the projection corresponding to the set -1, 1. Okay? That is equivalent to saying x power n x is less than or equal to norm x. Okay? That is equivalent to saying this x power n x is just bounded. Is bounded. This set is bounded set. Or the vector x power n x is non-bounded. Okay? So this is a nice criterion. You want to talk about something in spectral projection -1, 1. That is equivalent to saying some sequence is just bounded. Okay? So that is something very nice. So proof 1 implies 2. Okay? So x is in that projection. So we have that criterion. So this is the first thing we proved for A and B. We proved this, no, x, x, x. For if something is in A and B, then that is true for 1 and -1. So now minus x square is then equal to this we proved. Okay? This is equivalent to saying x as an operator is less than 1, greater than -1. I mean, all these things are -1, 1, they are all self-adjoint operators. We can make sense of all these things. X is greater than -1, x is between 1, right? And then we take x is in this, and x -1 is okay. This is the first statement. I just rewritten the statement. I applied the positivity. I mean, the definition of positivity. Definition of positivity is this x, x, x greater than or equal to 0. But here 1 minus x is greater than 0 or x plus 1 is greater than 0. All the, I mean, it is just that. I mean, the inequality partial order is just the, you just take it to the other side, greater than or equal to 0. That is just the positivity. Okay. So this is just written in this. So the point is if some x is between B and A, for self-adjoint operator, then the spectrum of x is contained in AB. This the same trick we can use, or we have already proved that if x is greater than 0, then the spectrum of x is contained in 0 infinity. So if x is minus something is greater than 0, then the spectrum is contained in that corresponding A infinity. Then you apply the spectral mapping theorem for the linear polynomial, something x minus A or x plus A, whatever. Then you get this. Okay. So this is just what we have done earlier. For the positivity, we have proved that for positive operator, spectrum is contained in the positive real line. So you apply that and spectral mapping theorem, this is equivalent to saying sigma of x not equal to saying one way. This implies sigma of x is contained in -1, 1. Correct? Okay. This in particular implies that norm x is less than or equal to 1, which is equal to spectral radius. Right? This is spectral radius, which is equal to 1. Norm x is spectral radius, that is equal to 1, less than or equal to 1. So this certainly implies that, then of course this implies norm x power n is also less than or equal to 1. So norm x power n is less than or equal to norm x. What I have written? No. So you people didn't object to what I've written. I have written something nonsense. I mean, this is true only for this x, no? So what I have said is not correct. Okay. Now you consider this x naught equal to this 1x. I hope you are listening. Okay. So this operator, I apply this operator. Okay. So this, whatever I have written is equivalent to, this is only for this x x in this subspace. Okay. So this is true. So x naught xx is less than or equal to, I mean, once you write this, then it is true for, well, I don't want to write that. See, you can consider x naught. Okay, maybe I have to do that. X naught is just the restriction. You can write it, but that is getting unnecessarily complicated. What I want to say is, this is x naught is just an operator restricted to this subspace. Okay, I mean, you don't have, you can hit it with this projection. Then that is an operator on the big space. But without that, you can restrict to this Hilbert space, this subspace. Okay, on this subspace, this inequality is satisfied. So on this subspace, I mean, I don't like it, but to reduce the complication, I have to write so many lines. Okay, this is just the x restricted to this subspace. Okay, as an operator. See, notice that it commutes with this. Okay, so mx minus 1 1 is invariant. So x leaves this space invariant. It's not, it's reducing, and it's also, the star is also invariant, star is itself. Okay, so it is invariant. So you can restrict that. You can restrict this x to that. On this x naught satisfies this relation. Okay. So by the earlier argument, this implies x naught is less than or equal to 1, greater than or equal to minus 1. So the spectrum of x naught as operator on this subspace, okay, is contained in minus 1, 1 by the positivity argument which I have gone through. Okay. So this implies norm x naught is less than or equal to 1. And norm x naught power n is also less than or equal to 1. Okay. Now x naught power n, which is same as x naught power x power n x is same as x naught power n x, because x itself leaves the space invariant for x in this. Okay. Since x naught x leaves this space, so this is true, which is less than or equal to norm x. Okay. Okay, no mistake. Okay. This is fine. Anyway, go through it. I have written all the arguments here. I mean, except my handwriting, everything is clear. So, well, I read some of your reviews. Not all of you are here for the past semester. Some reviews are good, but some says that my handwriting is not good and all those things. I'm sorry, I cannot avoid much. But I think I have written it and writing it better this time. Okay. I mean, my handwriting is usually not good, but then this is the first time I'm writing in iPad, so it's worse than what it used to be usual. So I think
It's a doubting thing. I asked on the group, and Tuesday, they seem to agree on Tuesday.
say it again.
They seem to agree that Tuesday will be great if you like for clarifying doubts regarding the miss.
No, you are talking about this or something else. You are talking about the maths here.
No, no. So next week you said like one day might be free. So people seem to agree on Tuesday.
You will tell you on Tuesday. I am not hearing properly. I'm sorry. What did you say? Say it again.
So I said like people like so people agree on Tuesday, like Tuesday taking an extra class on clarifying questions.
Oh, you want you about the next week you want to talk about, no?
Yeah.
So you want to take it on Tuesday. Okay.
Tuesday,
Yeah. So suddenly it's talked about different topics, so I got confused. Okay, fine. So we will meet next Tuesday. Okay. Okay. So this proposition one implies two is proved. Okay. Now we want to prove two implies three, which is clear. It is just bounded. Okay. If it is less than norm x, it's bounded. Okay, that's clear. So x and x is bounded. Now we want to prove 3 implies 1. Okay. So 3, the assumption is suppose this, we don't need norm, we can just write it as x power n x n in n is bounded, is non-bounded, okay, in the Hilbert space. Then we want to prove x is in that, x is a spectral projection corresponding to that interval -1, 1. Okay. Okay. So why is that true? Suppose it's not the case. So we want to prove it is in the so we want to prove x is in mx of -1, 1. Okay. So let we take the projection of this. Okay. That x naught equal to this 1. Did I interchange? Yeah. 1 -1, 1 of x acting on x. Okay. We want to prove x is in this. That is, we want to prove x equal to x naught. That's what we want to prove. Okay. We want to prove that x is in that. That means x equal to x naught. That's what we want to prove. Okay. Now let us consider x minus x naught. What is x minus x naught? Which is just x minus 1 -1, 1 x of x, right? That is equal to, this is just identity times x. So which is equal to 1 real line minus this -1, 1 times x, right? Okay. So now I make the following claim. Claim is 1 r minus, I increase it slightly, this interval, by adding a 1 minus 1 by n on the left side and 1 plus 1 by n on the right side. Okay, is equal to 0 for all n. Okay, if the claim is true, then we know that 1 or this 1 minus minus, I mean this set goes to 1 minus 1 plus 1 by n. This set converges to in L infinity, okay, in mu or whatever. It's almost everywhere, okay. Converges to this 1 or minus 1, okay, as functions. Okay, so this implies the corresponding, you can, I mean, I'm just removing it, right? And remove it, of x converges to x strongly. Okay, so this times x equal to 0 for all x means that that is also equal to 0, right? We want to prove this is equal to 0. We want to prove x equal to x naught. We want to prove x minus x naught is 0. So which is equal to this projection applied to x. I want to prove that this sequence which converges strongly to this projection, this applied on this x is 0. Okay, if that is the claim. If the claim is proved, then this sequence of projection converges to this sequence. Okay, then this since this converges, x equal to x. Okay, so if the claim is proved, then we just have to prove this claim. So let us consider this claim. So what is this claim? 1 or minus 1 minus 1 by 1. So this is just 0 minus this, 0 plus this. Okay, and let us this x acting on x. Okay? Now this norm is greater than or equal to 2 times, no? Which is just epsilon. Which is, yeah. So 1 plus 1 by n times norm x. This is the third statement which you have used several times. So it's here. The third step. Here. Right? X minus T0. T0 equal, take T0 equals 0 and epsilon equal to 1 plus 1 by n. Okay? We are applying to minus 1 by n, 1 plus 1 by n for that. Epsilon equal to 1 plus 1 by n and T0 equals 0. I'm just applying to this. By applying to this, I'm getting this. Okay, this is greater than this. Right? Okay. I'm sorry. There is a x here. Okay, this is what is x naught. Right? Now you consider xm x. Okay? You have assumed that this is bounded. So if we have a x in x is in minus 1. What's the time? So we have 15 minutes. So if we, is this fine? Are you following? We have x power n, x is bounded. That's what our assumption is. Okay, I want to contradict that assumption. If I'm claiming that this is the claim is this projection applied to x is 0. Okay, that is the claim. So suppose if it is not equal to 0, okay, suppose that projection is not equal to 0, then I want to say that it's, is x power m x. I want to contradict this. X is in we have this inequality. Can you see why this contradict this? Can anybody see this? So are you following? Shall I start from the beginning? We want to prove the following. We want to prove some x is in the spectral projection of this that is equivalent to saying this.
Yes.
This is
There is key is not.
huh? What is it?
Visible.
Nothing. The screen was not visible. Now it is okay.
Yeah, there's somehow something happens. If I touch something, something happens. Now it's okay, no?
Yes, sir.
So we want to prove. Let me write it and then come back to you. Okay. So now this 1 plus x is something. It's okay. This is just greater than that. No, it need not be. I was wondering why is that equal. Okay, this is certainly greater than this. Okay, I can put a projection here, no problem. I can put any projection here, then this will work. Okay, so that's just this. Minus 1 by n, 1 plus 1 by n. Of this x. I can put any projection here times x power m x. This is okay. I will go through the whole argument again. Okay. Now this is greater than or equal to. This is equal to. We can bring this projection commute with this, so you can bring it here with the x and x power m. All these things makes it invariant. So each time you will get a 1 plus 1 by n. Okay. Each time you get 1 plus 1 by n power m. Okay. Times norm x. Norm x, no? Norm x. Okay. So this will not be bounded. This is the condition. Let me go through this again. Okay. So what is our proposition? Our proposition is we assume something is self-adjoint. Then we want to prove x is in this spectral projection corresponding to this interval minus 1, 1 is equivalent to saying the third condition. We are only proving the third condition. This norm xn power x is bounded. Okay. Now we are proving 3 implies 1. So xn, we assume that xn x, norm xn power x power n x, that set is that sequence is bounded. Okay, we assume that. We want to prove that then exists in this spectral projection. It is equivalent to saying if you hit by the spectral projection, it is equal to that. Okay, which we denote by x naught. Okay, now we want to prove x equal to x naught. So in particular, we want to prove x minus x naught is equal to 0. So x minus x naught, we have written it as this projection like this. This indicator function r of r minus minus 1 1 x, something like that, which is actually is the limit of 1 of r 1 minus 1 by 1 by minus 1 minus 1 by n 1 plus 1 by n. We have written it like this using this here. Okay. So now this is, and the claim is this is 0 for all n. Okay. If this is 0 for all n, then this should be 0. Suppose this is not equal to 0 for all n. Suppose this is not equal to 0. Okay. So that I should have written somewhere. Okay. Maybe I will just remove this. Okay. Now, so we have proved that we have, if the claim is proved, then we are done. Okay, that is clear. So suppose that is not equal to 0, that whatever that 1, that r minus whatever minus 1 by n 1 plus 1 by n of this x acting on this x is not equal to 0 for some n. Okay. So then this is true. Okay. This is true always, but if x is, this is not equal to 0, so then this is true. Okay. But then this x power mx, you can write it, you can use this projection and which you can bring it here. Okay. And by this inequality, this is greater than or equal to this. And we assume that this is not equal to 0. Okay. and x is also not equal to 0. So this is this, but then this sequence 1 plus 1 by n power m is unbounded in m, right? So our x power mx is unbounded, which contradicts the 3 implies. I have given all the argument, but if you don't follow, you tell me, either now or on Tuesday. Okay? If someone wants to say something. Anyway, this is a nice, the criterion is proved, and this is a nice criterion. You want to prove something in the spectral projection, it is enough to prove some sequence is bounded. So you will see immediately how this is very useful. I will prove this proposition corollary and then stop. Okay? So first statement is x is in mx of some t0 minus epsilon, t0 plus epsilon, okay, is equivalent to saying x minus t0 divided by epsilon. This operator applied on x, okay, power n, n in n, is bounded. Okay. So this is the corollary one. Just apply to, I mean, I have already told you that this is true, no? M x of some e, yeah, it's okay, is same as m p of e of p of x. There is some assignment you are supposed to do. You just use that assignment and apply to this. Apply the proposition, earlier proposition to this operator, x minus t0 by epsilon. That's all. Okay. If you apply that, then that will, this corresponding projection, whatever this t0 minus epsilon, t0 plus epsilon, this interval, if you just shift it, it will become minus 1, 1. Okay. It's because of that. Why it's happening? Okay. So you just apply to that. Second, if y is an operator with commutes with, should it be self-adjoint or something? No, there is no need. Commutes with x. Any operator need not be self-adjoint. Commutes with x. Okay, y is some operator with commutes with x. Then y leaves mxi for any interval I, for any bounded interval, leaves mxi invariant. For all bounded I contained bounded interval. Okay. Okay, fine. So proof. So y commutes with x. First thing is, so we have to prove x is in mxi, mx. So we can take the interval to be t0 minus epsilon. First, let us prove it for closed interval. Okay. So first, let us prove it for closed interval. Then we will come to open interval, half closed interval. Although this interval is any interval. Okay. For any interval, closed or open or whatever. So first for closed interval. Close. First assume I is closed. Then suppose x is here. We want to prove that y leaves this invariant. So x is here in this interval is equivalent to saying x power n x n in x power whatever, we have to shift it, no? X minus t0 by epsilon power n x is bounded. Okay. But then y is a bounded operator. So y times x minus t0 by epsilon power n x. This is also bounded because y is a bounded operator. But then y commutes with x, it will commute with x power n and all those things. So this is same as x minus t0 by epsilon whole power n yx. This is bounded. But then something is bounded. Here the vector is yx. So this is equivalent to saying yx is in that. You can see how this criterion is very useful. This is almost criterion actually. I didn't write it, you can mention it. Okay. So this is for closed interval, but for any open interval, you can approximate it by closed interval, and any half closed, half open interval, you can approximate it by open interval. I don't want to write it. Okay. But then if you approximate as sets by open or closed interval, the corresponding indicator function will converge, then the corresponding projection will converge, so you can prove it. Okay. So I don't need to prove. If I mean you have to prove the invariance, so it is exercise. Approximate. Right. It's not assignment, just exercise. Approximate other intervals by closed interval. Hence the corresponding projections. Like that is very bad. Okay. So then you will prove. Okay. That's all. So any question? Anyway, you can ask. We'll meet on Tuesday, and you can ask this question. Okay. Bye. I'll end the session.